China claimed their stealth bombers were invisible. The H-20 program, years of development, billions invested. State media broadcast renders showing aircraft that looked like the American B-2 Spirit. Beijing called it a strategic game changer, a platform that would penetrate enemy air defenses undetected, the key to projecting power across the Pacific. Then radar analysis revealed the design flaws that make true stealth impossible with China's current technology. This video exposes why China's stealth bomber program faces fundamental problems that no amount of investment can solve, and why Western air defenses will see them coming long before they reach their targets. China's H-20 stealth bomber program began in the early 2000s. The goal was clear: develop a strategic bomber capable of striking targets across the Pacific without being detected. Range estimates suggest 8,000 kilometers. Payload capacity projected at 10 tons of precision-guided munitions. Subsonic speed was optimized for fuel efficiency and a reduced acoustic signature. The design borrows heavily from American stealth principles. Flying wing configuration eliminates vertical stabilizers that create radar returns. Smooth surfaces reduce reflection angles. Engine inlets are buried deep in the fuselage to hide turbine blades from radar. Chinese state media released computer-generated imagery showing an aircraft nearly identical in appearance to the B-2 Spirit. The message was intentional. China now possesses the same capabilities as the United States. In 2018, the People's Liberation Army Air Force announced the H-20 had entered testing. Grainy satellite images showed what appeared to be a large flying wing at a test facility in central China. Aviation publications speculated about performance specifications. Defense analysts warned of a strategic shift in the Pacific balance of power. Beijing remained silent on technical details. No official specifications were released. No photographs beyond distant satellite shots. The secrecy fueled speculation that China had achieved a genuine breakthrough in stealth technology. But stealth is not about appearance. It is about materials, manufacturing precision, and radar cross-section management across multiple frequency bands. And in each of these areas, China faces obstacles that computer-generated imagery cannot overcome. True stealth requires more than shape. The B-2 Spirit's radar cross-section is estimated at 0.075 square meters from certain angles, smaller than a bird. This is achieved through a combination of design, materials, and manufacturing tolerances measured in fractions of millimeters. The airframe uses radar-absorbent materials that convert electromagnetic energy into heat. Carbon composites are layered with specific densities to target different radar frequencies. The skin is not painted. It is treated with coatings containing microscopic particles engineered to scatter radar waves. Panel gaps are filled with conductive tape. Fasteners are designed to sit flush. Every rivet, every seam, every surface discontinuity is managed to prevent radar reflection. The manufacturing process requires clean rooms, precision tooling, and quality control standards that took American industry decades to develop. China does not have this manufacturing infrastructure at scale. Satellite imagery of Chinese aircraft production facilities shows conventional assembly methods, open-air construction, standard industrial buildings, no evidence of the specialized clean rooms required for stealth composite layering, no indication of the testing chambers needed to validate radar cross-section performance across frequency bands. This is not a criticism of Chinese engineering capability. It is an acknowledgement of the industrial base required to produce stealth aircraft. The United States spent 30 years and hundreds of billions of dollars developing this infrastructure. China is attempting to replicate it in a fraction of the time with a fraction of the investment. The result is an aircraft that may look stealthy, but does not perform as a stealth aircraft. Radar cross-section is frequency dependent. Stealth aircraft are optimized against X-band radar, the frequency used by fighter aircraft and missile seekers for targeting. The B-2's shape and coatings are designed specifically to defeat these systems, but longer wavelength radars, VHF and UHF bands, can detect aircraft at extended ranges. The trade-off is resolution. These radars can tell something is present, but cannot provide the precision needed to guide weapons. Western air defense networks combine multiple radar types. X-band systems provide targeting data. VHF systems provide early warning. Integrating both creates a layered defense that detects stealth aircraft early and tracks them continuously until shorter range systems can engage. China's H-20, if it performs as Beijing claims, would be optimized against X-band radar, but Western VHF early warning systems would detect it hundreds of kilometers away. By the time it reaches X-band engagement range, defending fighters and surface-to-air missiles are already positioned. This is the flaw that computer-generated imagery cannot hide. Stealth works when one side has it and the other does not. When both sides understand the limitations and deploy countermeasures, the advantage shrinks. Western air defenses have been preparing for Chinese stealth for decades. China's stealth materials face another problem: durability. Radar-absorbent coatings degrade with exposure to moisture, temperature variation, and mechanical stress. The B-2 requires extensive maintenance after every flight. Panels are inspected, coatings are reapplied, surface treatments are refreshed. This maintenance is not a design flaw, it is the cost of maintaining stealth performance. The materials that absorb radar also break down under environmental exposure. Keeping an aircraft stealthy requires continuous upkeep in controlled conditions. China's H-20, if it uses similar materials, will face the same maintenance demands, but the infrastructure required, climate-controlled hangars, specialized coating facilities, and trained technicians represents an enormous logistical burden that China's Air Force has not demonstrated at scale. Leaked maintenance reports from Chinese aviation facilities suggest persistent issues with composite repair and surface treatment consistency. These are not catastrophic failures. They are indicators of an industrial base still learning how to sustain advanced stealth platforms operationally. An aircraft that requires 3 days of maintenance for every flight hour is not a strategic weapon. It is a demonstrator. The H-20's engine integration presents additional challenges. Turbofan engines produce an infrared signature that search and track systems can detect at long range. The B-2 uses extensively cooled exhaust mixed with ambient air to reduce its thermal signature. The inlets are designed to prevent radar from illuminating the engine face. Chinese turbofan technology lags Western equivalents in thrust-to-weight ratio and fuel efficiency. WS-10 and WS-15 engines powering Chinese fighters have faced reliability issues and performance shortfalls. A strategic bomber requires engines with greater fuel efficiency, a lower infrared signature, and higher reliability than fighter engines. No public evidence suggests China has developed engines that meet these requirements. If the H-20 uses existing Chinese turbofans, its range will be shorter than projected, its infrared signature higher, and its operational availability lower. And if the engines fail to meet performance targets, the entire aircraft becomes less capable than advertised, regardless of how stealthy the airframe appears. China also faces a testing deficit. Stealth aircraft require extensive radar cross-section testing across multiple frequency bands and aspect angles. This is not a one-time test. It is continuous validation throughout the development process and operational life. The United States operates dedicated radar test ranges with specialized equipment to measure aircraft signatures. China has built similar facilities, but the number and sophistication of these ranges remain limited compared to American infrastructure. Without comprehensive testing, there is no way to verify that the H-20 achieves the radar cross-section performance Beijing claims. State media can release specifications, engineers can project performance, but without validated test data, the numbers are estimates. Western intelligence agencies monitor Chinese test facilities. The absence of long-term, systematic testing suggests the H-20 program is either behind schedule or facing technical challenges that prevent full validation. The strategic implications are clear. If the H-20 performs as advertised, with low radar cross-section, an 8,000-kilometer range, and a 10-ton payload, it would represent a genuine threat to Pacific bases and carrier groups. Penetrating bombers could strike targets that previously required ballistic missiles, providing more flexibility and precision. But if the H-20 is detectable at extended range by VHF early warning radar, if its maintenance requirements limit operational availability, or if its engines produce excessive infrared signatures, then it becomes a conventional bomber with limited utility in contested airspace. Western air defenses are designed to counter both scenarios. Layered radar networks detect aircraft early. Fighter patrols provide response capability. Surface-to-air missile systems cover approach corridors. Electronic warfare systems can jam guidance and communications. The H-20 does not need to be a complete failure to be strategically irrelevant. It only needs to be detectable enough that defenses have time to respond. Current evidence suggests it is. China continues developing the H-20 despite these challenges. The program serves multiple purposes beyond operational capability. It demonstrates technological ambition. It signals strategic intent. It provides industrial experience that future programs can build upon. But demonstration is not deployment, ambition is not achievement, and strategic signaling does not change the physics of radar cross-section management. Right now, Western air defense networks monitor approaches to critical facilities. Early warning radar scans continuously. Fighter squadrons maintain alert status. Surface-to-air batteries cover key corridors. If a Chinese H-20 ever approaches defended airspace, those systems will detect it. The question is not whether it will be seen, but how far away detection occurs and how much time defenders have to respond. China can claim stealth. State media can broadcast computer-generated imagery. Officials can project confidence. But radar does not care about claims. It measures reflections. It calculates cross-sections. It detects aircraft based on physics, not propaganda. The physics suggests that China's stealth bomber, if it ever becomes operational, will not be as invisible as Beijing wants the world to believe. Subscribe for more breakdowns on why technological claims require validation, not just speculation. Share this with anyone who needs to understand that stealth is engineering, not marketing. And remember, in modern warfare, the side with the better sensors usually detects the threat first. Detection means the stealth failed.